Whoops. So, welcome to our first in a series of discussions about infinity. It's going to happen over the next 4 units. So, I think it's a pretty interesting part of mathematics. I hope you will enjoy it as well. But we're going to start with kind of reviewing your L'Hopital's rule. So, let's see if my pen works this time. So, L'Hopital's rule works if you're looking at a limit that yields either 0 over 0 or infinity over infinity. If one of these two situations happen, you can, instead of looking at these indeterminate forms, which is what they're called, you can instead look at the rate at which they're moving toward 0 or infinity. So this rate will yield how quickly they're actually getting there, which is going to be a ratio of that. So this is an important idea, and this is the whole ball of wax. That's it. L'Hopital's only works for 0 over 0 or infinity over infinity. But what we're going to look at in this video is the fact that there's there's 5 other indeterminate forms that we can use L'Hopital's on if we just rearrange them to look like 0 over 0 or infinity over infinity. So let's start here. First off, I look at x going to infinity, and right away a little light bulb comes on, and I'm thinking I might be able to use the idea of dominance, because dominance is related to the end behavior of functions. So if we're looking at the end behavior, in other words, as x goes to plus or minus infinity, we can use this idea of dominance. And what we know from the functions we know so far is our most dominant function, though we're going to be adding some to this, are exponential functions. And within that, the bigger the base, the more dominant. The next most dominant functions are algebraic functions. So things that look like power functions. But they don't need to be just integer powers. They could be square roots and a variety of combinations of algebraic style functions. Bottom of the dog pile are our logs. Logs beat no one. They don't even beat like square root of x. They are very weak. They're weak, sad little functions. And notice what's not in here is trig functions. Trig doesn't get a dominance because trig just makes things wiggle. So we look at this, we go, I bet I can use dominance, and I'm looking at it, that goes to infinity, that goes to negative infinity. The fact that it goes to infinity over negative infinity doesn't matter because really these are both plus or minus. The positive and negative doesn't matter. It's the unboundedness. Unboundedness. That's what matters about the infinity. So we go, we can use dominance. Oh, they're both algebraic functions. And within this algebraic function, the most dominant term is this, and the most dominant term is that. So we know our limit as x goes to infinity is 2x cubed over negative 3x cubed. They're now of equal dominance, and so we know it goes to negative 2/3. So using dominance whenever it's available, sorry, that's my phone ringing. Using dominance whenever it's available is definitely how you want to go. Here, when we plug in 0 over 0, because that's always your first line of defense, well, we know we can't use dominance. Let's see, tangent of 0 is 0, 0, 0, 0. Oh, that's 0 over 0. Oh, we're ready to go. We can L-hop this thing. L-hop. Here we go. So that's going to be the same as the limit as x goes to 0 of secant squared x minus 1 over 1 minus cosine x. We plug in 0. 1 over cosine squared, which is secant, is 1. We get 0 over, 0. Oh, we've got to go again. So I'm going to think of secant squared x. I don't have these memorized, so I'm going to think of it as secant squared x being cosine x to the negative 2. So now I'm going to look at my limit. And we are at negative 2 cosine x to the negative 3, chain rule, times negative sine x. Derivative of 1 is 0, over, that's going to be 0, negative, negative, sine x. Now the signs cancel. So it looks like really what I'm looking at is the limit as x goes to 0 of 2 over cosine cubed x. That goes to, oh, it's 2. Nice. So let's look at a few other indeterminate forms. So another indeterminate form is infinity times 0, because we don't know where that goes to. It could be 0, it could be infinity, it might be something else. So if we get 0 times infinity, it's very easy to turn it into something we can use L'Hopital's on, because 0 and infinity are reciprocals of each other. So we have some choices. We could either take infinity times 0 and turn it into infinity over infinity, or we could turn it into 0 over 0. So we have some choices, and so you want to choose what's easy. Don't make your life difficult. So we're looking at this first one, and right away, when I see something like infinity, I'm always going to have dominance in my back pocket. And I look at this, and let's see, I get infinity times 0 because this is a decay function. So to use L'Hopital's, I really should change it into, oh, this is going to be such an easy L'Hopital's, because I can change that into x squared over e to the 3x. The bottom dominates. That thing is definitely going to go to 0. I could have also thought about it just from here. Because I'm going to use this idea of dominance, who wins? Multiplication and division are actually the same operation. And so this guy is the dominant term. He's going to drag x squared to 0 with him. So even without turning it into infinity over infinity, I could have looked at this and said, dominance wins. This decay function is going to beat any lousy little algebraic function. He's going to 0. Okay, so what if we look at this one? Now we're going to 0, so we get 0 times negative infinity. So we have a choice. We can either change this into x squared over 1 over ln of x, because that would be the same expression, or we could change it into ln of x over 1 over x squared. Oh, this is a bad chain rule. I'm choosing this. So let's see, the limit, because now when I plug in 0, I get infinity over 1 over 0 is also infinity. Negative infinity over infinity, who cares about the negative? It's unbounded over unbounded. We can L-hop that. So the limit as x goes to 0 from the positive side. Derivative of ln of x is 1 over x. Derivative of 1 over x squared, I told you you'd get fast at these, is negative 2 over x cubed. We're going to simplify that. This division is the same as multiplying by the reciprocal. So we're at x cubed over negative 2x. Oh, that's negative 1/2 x squared. The limit of that is x goes to 0. That thing goes to 0. Let's take another look at this one. Now we're going to pi. Let's see. Pi minus pi, 0. Cotangent is cosine over sine. As we go to pi, the denominator goes to 0. Oh, times infinity. So that means I have a choice. I could either say x minus pi over 1 over cotangent, or I could say cotangent over 1 over x minus pi. Oh, this might look bad, but this is easy, because 1 over cotangent is tangent. Let's go with that. So the limit as x minus pi over tan x, as x goes to infinity, we're going to check it real quick. let's see, 0 over tangent of pi is 0, 0 over 0. We're ready to go. That's going to be the same as x goes to pi of the derivative of this. So 1 over secant squared x. Let's see, plug in pi. We're at 1 over secant squared, 1 over cosine, negative 1 squared 1. Oh, the limit is 1. Here's another indeterminate form, infinity minus infinity. Because infinity minus infinity could be any number of things. And so what I've tried to do for us is identify the tricks that come up most commonly. Common denominator is one trick. Log properties are another trick. And this is probably the most important for us this year because this is going to come up in the context of doing integrals. So I'm going to put a star by this, but let's run through one of these common denominator things. So we look at it, 0, 1 over infinity, 1 over 0. Oh yeah, it's infinity minus infinity. But a very quick trick is just to throw the common denominator. So x minus sine x over x times sine x. Plug in 0 just to check. 0, 0. Yeah, we're good to go. Let's L-hop this baby. So 1 minus cosine x over, little product rule, sine x plus x cosine x. Plug in x equals 0. Let's see, we get 0 over 0. Oh, we got to go again. Limit as x goes to 0 of derivative of this is going to be sine x over derivative of sine x. So we're at cosine x. Little product rule, derivative of the first, so cosine x. Derivative minus x sine x. We plug in 0. We're at 0 over, oh yay, the denominator is non-zero, and 0 over 2 is a perfectly good number. It's 0. Let's see if we can run through the log properties, and I'll open another video for the second part here. Infinity minus infinity. But these infinities can be very different sizes, so we need to analyze them a little bit better. So instead, we need to look at the limit of ln of log properties, 3x squared plus 5x plus 2 over 5x plus 6. The innards, as x goes to infinity, goes to 3/5 x, actually, if we want to keep track of it. So the limit of ln of 3/5 x, as x goes to infinity, this is going to go to infinity. Ln of infinity is infinity. And don't forget, that's not a valid answer on the AP test. Your answer is does not exist, or what they usually write on multiple choice is non-existent. Got another situation here. This time, when we take ln of the ratio of those two things, we get limit as x goes to infinity. The bottom dominates, so we get ln of 0. And ln of 0 is negative infinity. Whoop. And once again, your answer would be non-existent. But down here, now we've got the ratio we can see is going to be 1. So really, this is the same as the limit as x goes to infinity of ln of 1. Oh, that's 0. So this time infinity minus infinity was 0. But over here, we're at the ratio as x goes to infinity. And now, as we go to infinity of this divided by this, we're going to end up going to 8 over 27. So I thought I'd take this opportunity to say, here's how you're going to see it as a multiple choice answer. We're going to notice these are perfect cubes. So it's going to be 3 ln 2 over 3. But the other thing they usually do is they don't leave fractions. So it is likely they would change this into 3 ln 2 minus 3 ln 3. I'll meet you in the next video.